energy seminar. And today our first speaker is Cowperthwaite. And Phil is currently a fifth-year graduate student at Harvard, working with Professor Edelberger on the time domain science. And he got his bachelor's degree from University of Maryland. And he has published 26 papers, and 7 of them are first authors. And his research interest is currently on the follow-up of gravitational waves using traditional optical telescopes.
Thank you. So thanks for the opportunity to come and talk about some of the exciting work that we've been doing. It's the stuff I've done with Ito's whole group and members of the Dark Energy Survey, who are collaborators of ours. So I'm going to give this talk under the assumption that you've probably seen a lot of recent talks about gravitational waves and LIGO. So in the interest of time, I'm going to really just move sort of ahead quickly. So this was the landscape before this event of LIGO detections. We had a series of basically 4 and 0.9 now detections of merging black hole binaries of a variety of masses. And that's really exciting because it shows that LIGO works and that we can detect gravitational waves directly. But if we really want to do EM follow-up, we're really interested in what happens when neutron stars merge, or a binary that has at least one neutron star. So we got the opportunity to do that on August 17th. The detection of GW 170817 is a binary neutron star detected by LIGO and not by Virgo, which we'll see is useful in a second. So this is the frequency power, basically time plot. It's really cool because binary neutron stars spend much more time in LIGO's bandpass than, say, the binary black hole merger. So we actually get 3,000 orbits of the system. You can see the signal slowly building up to the chirp where we detect it. It's cool because it's the most significant gravitational wave detection we've made at 32 sigma, the false alarm rate of less than once per 80,000 years. And just some basic system parameters. Total mass around 3 solar masses, one around 1.4 to 2.3. The secondary around 0.9 to 1.4, and a pretty wide range in mass ratio. So now we can take that original mass plot that I showed, and now it looks like this. So this is now the current landscape. So we have all the previous, blue are the previous LIGO detected black holes. These purple are sort of X-ray binary black holes that we've detected observationally prior. Then we have the population of neutron stars. So we have known neutron stars, just through pulsars and the like, and then these orange ones are the first LIGO neutron stars. But what makes this really, really exciting is this. So just 1.7 seconds after the LIGO trigger, Fermi, GBM, and Integral both detected a short gamma ray burst associated with this event. And that's really exciting because that makes this truly the first gravitational wave EM multi-messenger event. And we always talk about this, multi-messenger astronomy, joint gravitational wave, electromagnetic astronomy. But it's important to understand why we care about these things. So these are some of the benefits of doing joint astronomy. So it's really necessary for any of these gravitational wave detections that if we want to maximize the science gains, we have to find an EM counterpart that we can associate with the event. So this allows all kinds of cool stuff. We can do precise localization at distance measures, so we can get redshifts. If we can identify a host galaxy, which is likely in the LIGO volume, then you can do all kinds of stuff that we do with other populations of transients, like supernova and gamma ray bursts, where we do demographics, population studies, what kind of stars are they associated with, just all kinds of insight into the environment of the transient. And then also what we'll talk about today is that modeling of the light curve and the behavior allows us to infer something about the ejecta properties, its compositions, energetics, all the physics of the system itself. So if we want to chase an EM counterpart, we have to know what one looks like. So we have this whole zoo of counterparts of interest. So sort of the big one that would be the easiest to directly identify is a short gamma ray burst. So a lot of work was done by Wenfei Fang when she was here as a graduate student on associating short gamma ray bursts to compact object mergers. So that's one thing we'd really like to see, and we did see it. That's great. If you do have a short gamma ray burst, then you have this whole afterglow game that we can play. So either if we're looking down the barrel of this relativistic jet, which is collimated and beamed towards us, then we should see an on-axis afterglow. You can see that in X-ray optical and radio. If we're slightly off-axis from the jet, then eventually it'll decelerate and spread out, and we can see an off-axis afterglow, also in X-ray optical and radio. Then the one we really want to focus on today is the KILONOVA, which is this isotropic optical near-infrared emission, which is basically expanding ejecta powered by the radioactive decay of heavy elements that are synthesized in the ejecta. We'll talk about that more later. A famous early example of this is GRB 130603b, where Hubble observations at plus 10 days saw excess near-infrared flux well above what just the afterglow model would predict. So we did this for GW 17817. We went out and researched this localization region. So we found out early that day, so that night, within 12 hours, we could begin searching. And it was really fortunate because due to the detection by LIGO and the non-detection by Virgo, we were able to very well localize the source to just 30 square degrees. So you can see that here on this plot by Leo Singer in comparison to early binary black hole localizations with just LIGO, where you had maybe 1,000 square degrees to cover, or the more recent 170814, which was the first binary black hole merger detected by all three instruments, and that was only 60 square degrees. So this was great. This is doable. So pretty much everybody who had a telescope in the south that could look at this did. And an optical counterpart was quickly discovered by several teams, including our own DECAM observing team. It was first announced as SSS-17A by the Supernova Survey. So this is the DECAM discovery image. So this is a GRZ composite image taken from images captured about half to 1.5 days after the event. You can see this bright optical transient, just about 10 arc seconds or a few kiloparsecs away from the center of this galaxy, which is NGC 4993. It's very rapidly fading because here's basically the same set of observations 2 weeks later, and you can see that it's completely gone. So once this candidate was identified on the very first night, pretty much every telescope in the world that could see it tried to look at it, including our program, where we had 2 weeks of observations. We also had follow-up out to 20 days with Gemini and Hubble epochs. And if you put that all together, you get this light curve. So this object's pretty striking to begin with. If you look here in U and G band, it declines very, very rapidly. So it's about 17 and change on the first night. And just a few days later, it's down 2 magnitudes. So that's a really, really incredible decline in the blue bands. You can see it reddens over time, where we have it stays bright out through Z and Y and H band. And it's even detectable in K band with Gemini out to 18 days. And really, the only reason this light curve stops is just that it was too close to the sun, so we couldn't keep observing it. I think we definitely would have kept following it until it was truly gone in K if possible. There's a lot going on here. So you can see its behavior in sort of subbands here. So here's the very blue behavior. We have this very rapid decline in something like DS, DECAM G band, I band, and then H band. So we want to fit this model. We want to see if it actually does behave like we expect for a kilonova. So we did that using sort of modified our net model from way back in the 80s, and we fit this using MOSFET, which is developed by James Gidishon and others here, to do basically an MC multiband fit the light curve data with this model. Key parameters that we consider are nuclear heating. Is it actually our process heating, or can you explain it with something like nickel 56 in a traditional supernova context? What sort of ejecta masses and velocities, what are the energetics of the system? And then what is the gray opacity? So those are really the key things that we look at. So the first thing you can do is just say, does it behave like a supernova? The answer is really no. So this is just a very basic nickel 56 powered model. It really fails to capture a lot of the key near infrared data. It's way off here. Most also unphysical is that it requires 75% of the ejecta to synthesize nickel, which is much, much, much higher than we see in actual supernova. It's closer to a few percent. So this model really doesn't do a good job. So we really want to then turn to kilonova models.
Phil?
Yes?
Is there no K-band data prior to those points?
Not in our observations. No, we'll get to that. But yeah. So these are H bands that were basically acquisition images for spectra, and then K-band later. But you'll see. We'll talk about this later. So just to quickly sort of talk about the history of kilonova models. So as I said, a kilonova is like a really faint, short-lived transient. It's much similar to supernova, but powered has much lower ejecta mass, much higher velocity, and different heating schema, as these R process elements have very different decay properties than nickel 56. So the actual, what you observe, or what you think you'd observe in a kilonova, depends heavily on basically the composition of the ejecta and how efficiently it can synthesize these R process elements. So there's really many different models that people have explored in the literature. So this is a nice little infographic by Brian Metzger that kind of shows the evolution of these models. The very early late 90s Leon-Pazitsky model, which just was very bright and very blue. And they just had this basic parameterized heating. Brian Metzger came by and did his R-process heating calculations for actual R-process mixture. But he used low opacities, similar to what we see in supernova. So he had a very blue transient. Then Barnes and Kaysen came along and argued that these R-process transient opacities are actually much, much higher. So the transient's even fainter and redder. And then there's been other suggestions of ways to get blue and ultraviolet. So this is why models are really important. And this sort of creates this sort of false dichotomy between kind of blue versus red kilonova, when really I think it's better to think of it as blue and red kilonova. So this is another nice little graphic from Dan Kaysen and Brian Metzger, where we consider different progenitor systems. So you have two neutron stars or a neutron star and a black hole. They merge, and you have various remnant scenarios. So you have a hypermassive neutron star that lives for some amount of time, then collapses into a black hole. Maybe it lives, you have some rapidly rotating neutron star that maybe lives forever. You have just prompt collapse to a black hole or to a spinning black hole. And these are just graphics of the various mixtures of red, blue, and ultraviolet emission that you might expect for each of those scenarios. So really you can see that in all of these, you expect at least a little bit of both. So it's best to consider a kilonova model that also has sort of red and blue ejecta. So we fit that, you get something like this. So you can see this does a much better job of modeling a lot of the light curve behavior than other models I showed. So do very well in the blue, captures this hump through the Z and the Y band data, but it does overshoot the H and sort of takes a while to catch up with the K, and you can see that behavior here. The overall ejecta properties are that sort of the total mass is about 5% solar, with the bulk of it in the red component. The blue component is very rapidly expanding, which 0.3 C, it's very rapid, and 0.1 for the red component. But we also maybe want to consider, can you keep stacking on components and get closer? So this was sort of proposed by Tanaka last summer, basically this summer, 2017, where you can actually have 3 sort of distinct opacities in your ejecta, and that does a pretty good job of matching what you see in more complicated spectral modeling. So you have this blue component, which is low opacity, 0.5. You have this intermediate component, which is a moderate opacity. And then you have this high opacity material where you're producing lots of R-process elements, so it's much harder. So we did something similar where we basically produced a 3-component model and attempt to fit that to the light curve. That looks like this. So it looks very similar. A little bit of early time behavior is different, but it's basically functionally identical to the 2-component model. But roughly same amount of mass, an ejecta structure, and then the opacities. So what's interesting, though, is that this is what we were able to do really with our data. But it's important to note that there's a worldwide campaign. Dozens and dozens of telescopes and teams took observations of this event. So really, what can we do with all of that data? So this is what Ashley Villar here did sort of immediately after the announcement. So they compiled all of the publicly available data for GW 170817 from the Open KILONOVA catalog, which is these open transient catalogs that James Guillauchon maintains to compile all the public data for a given source. So you can take that data, you can homogenize it, you can do things like correct for systematics because you have different instruments, you have people using different reduction techniques, you can get rid of repeated observations, etc. And if you do all that, you actually end up with 625 data points spanning from 12 hours to 30 days. And we can fit this component, we fit this data with the 3-component model. So I really want to highlight this paper by Ashley because she put a lot of work into getting it out very quick and a lot of work into producing the data set. So if we fit that, you end up with something like this. So this is basically from Swift W2 all the way up to Gemini K. You can see, so here's all your K observations. And it's nice because data fits very well. Solid lines are realizations of the model, and then the shaded regions, sort of the 1 sigma error. If there's multiple lines, say in the example of U, that's because there's multiple variations of U band from different instruments. But in general, does a very good job. So this fits very similar, has a very similar velocity structure with a very rapid blue component, an intermediate velocity intermediate component, and a low velocity red component. The total mass is a little bit higher than previously, but that's okay. But there's a lot going on in this plot, so I think it's actually best to look at it broken down by band. So again, these are the same bands from the previous plot, but one panel per band, and then also the individual subcomponents are shown. So you can see in, say, the blue or swift band, you really just have this blue component, and then as you move towards redder bands, this purple component starts to come up and produces this hump that we see in the data, and then you have this red component, which is there, which is necessary to capture this behavior here, but is actually subdominant. So the bulk of the material is in this purple component, which I think is really interesting. So the other thing that we want to talk about with neutron star mergers is heavy element production. So it's been a really long-standing idea that binary neutron star mergers are one of the really dominant sites for our process production, and this dates way back to the 70s. So you can see that the actual ability of a binary neutron star to contribute to the observed R process abundance does depend on not just how much material it puts out, which is obviously important, but what's the composition of that material. Do you produce heavy enough elements? So for example, this was an adaptive plot by Tanaka, but originally in this 2014 Langer paper, where you can see the amount of material produced as a function of the electron fraction, which tells you for high electron fraction, it's difficult to produce a lot of R process elements versus for lower electron fraction. So you can see this blue component, which we can think of as our blue component in our model, really doesn't even get past 55 atomic number, whereas the lower opacity material can produce out to the lanthanides, which is this green line here. This region is the lanthanides. And then if you really want to get out to the heavy stuff like the actinides, you have to have low material. So the important thing is, just sort of run through this quickly, is that the ejecta masses that we infer from our models are consistent with what's necessary for binary neutron stars to be dominant sites of our process production. It very much depends on what you think of as your rate and your production rate, but in general it falls to be about 0.01 to 0.1 solar masses of material. So our 0.05 is right in the middle of that. So then mostly it's opened up to questions, so just conclusions. This event, GW 1717, was the first true gravitational wave and multi-messenger event. That's really exciting, because it means we can finally tackle these sorts of joint astronomy issues. The optical transient that we observed was consistent with an R process powered kilonova with a total mass of about 5% solar and velocity ranging from 0.1 to 0.3. This was confirmed both photometrically and spectroscopically. So there's two nice spectroscopic papers by Matt Nichols and Ryan Chornock covering the optical and near infrared. If you're interested about that side of it. But being that it is just one event, there's a lot of questions. First of all, the big one is how ubiquitous are these features? This source was much bluer and much brighter in a lot of senses than we had originally thought. So do we see that every time? Is it a viewing angle effect? Are there other physics that control that? And then, is the ejecta properties consistent across all mergers? Do they all produce about the same amount of material? So they can explain our process abundances. Do some produce more? Do they produce less? How do we fit these into explaining the observed abundances? And then there's just lots of other stuff about, what are the true R process heating rates? What are the true behavior of these opacities and the spectra? So there's a lot to do. It's a very exciting field. So leave it open to questions.
What is the total energy release of this kilonova?
So if you just do half mv squared, it's like 10 to the 51. Or,
Same as a supernova?
yeah. That v squared helps. It's not much mass, but that v squared helps. Yeah.
What's the current thinking? I should have been following archive papers and what have you, but for the delay of the Fermi interval,
Oh, this 1.7 second offset. So I think that's just explained by the fact that the gravitational waves are not impeded as they propagate out, whereas the jet in the material has to in some way pass through all that ejecta and break out. So I think that's probably the simplest explanation. Is just there could be other stuff like there's maybe some slight delay. This does not explain the 1.7 seconds, but there can be other sub-factors, like maybe it doesn't promptly collapse to a black hole. Maybe it spends some amount of time as a hypermassive neutron star, then collapses, then you drive a jet from accretion or some amount of ejecta to break through. So it's not so large that it raises questions about.
Does the frequency of GRBs versus the number of these, well, the one detect, does that mesh with each other okay at the moment, or are there still some discrepancies? So basically, given the number of GRBs, are they detecting enough gravitational wave sources?
I think so, because there's a lot of issues that go into this with Swift, because Swift only say something like Swift GRBs, it only covers so much of the sky, and then it has to be beamed. So I think if you make all those corrections, it's not seeing one is still pretty actually spectacular. I think there are some expected that might take 10 years to see a GRB and a gravitational wave signal at the same time, because there's all these competing factors. Yeah.
So if 2 components is good and 3 components is better.
That's just ridiculous.
I mean, fit this with a spectrum. I mean, the parameters seem to be sort of ordered in velocity and mass and kappa. So can you just make that kind of a power law range for all those?
I think it'd be more likely what you'd want to do is move to something like a more complicated single or 2 component method instead of just keeping stacking free parameters into your model. Do something like more of a 1 component, but maybe the opacity changes as a function of time and position or something like that versus just keeping stacking on.
I mean, it did seem like the IR data were not awesomely fit even with the 3 components.
Yeah, so there's still some issues of, for example, say overshooting the H band, but it's not clear if that's either a misunderstanding of, say, late time behavior in say, energy injection, or if there's spectral features. Because models by Ryan Wooliger have an absorption feature around where H band is, so spectral features like that could throw off your Likert fit. There's a lot of work to do, I think, on understanding exactly how these models behave. But oh yeah.
How long till the neutrinos get done?
A couple months ago.
Our second speaker is Dr. Anna Rosen, and she is a NASA Einstein and ITC fellow at the Harvard Smithsonian Center for Astrophysics. And by the way, she is the only Anna here. Everyone else goes by Anna. Anna did her undergraduate study at the UC Berkeley, and she got her PhD from UC St. Louis. Her research interest mostly focused on the theoretical and computational astrophysics with an emphasis on star formation.
Thank you. So today, oops, let me get this one. Today I'm not going to talk about star formation. I'm actually going to talk about, oh, is this not on? Okay, it's recognizing something. How does this?
Maybe turn on the mirroring.
What?
Turn on the mirroring.
Well, it worked before.
Yeah, I know it worked before, right?
No, but this is not turning on, right? No.
That should work. No, it's her.
Okay.
Now go for it.
Okay. Great. Thank you. Okay, so yeah, so today I'm not going to talk about star formation. Probably the one thing that this research has in common with my PhD research is the word cluster. So this is a work in progress. And let me just get this connected. But so today I'm going to talk about some work that I've worked on with several people here, including Lorenzo, who was a postdoc here and now a professor at Columbia. Blakesley, who's an ITC fellow. Katie, who was a pre-doc here. And then Enrico, who is a professor at UCSC but did his sabbatical here. And this project actually came out of collaboration here. And I'm going to talk about how we can constrain the hadronic gamma cosmic ray content in the Coma cluster. And so to go into that, that's not working. So first I want to talk about what are galaxy clusters. So galaxy clusters are the largest bound structures in the universe. They contain masses of about 10 to the 14, 10 to the 15 solar masses of material, mostly dark matter. And about only 20%, about 30 to 20% of the matter in these clusters is baryonic, and only a few percent of that is in the form of galaxies, while most of the baryonic matter is in the form of this hot, diffuse gas known as the intracluster medium. And the galaxy cluster itself is filled with this hot gas that is very low density, but very hot, that we can see in thermal X-rays. But it's also magnetized. It has it's about a few microgauss, which leads to the fact that the gas, the intracluster gas, is actually superalphatic. And so the nice thing about Coma, it's only about 100 megaparsecs away. And so it's been studied in many different wavebands. And so we've looked seeing both its thermal and non-thermal components. So the thermal component of the, okay, this is not working. Yeah. So the thermal component of the ICM is just this hot X-ray emission that's due to the thermal protons. So since the gas is at 10 to the 8 Kelvin and low density, we see about keV emission throughout the cluster. However, because of the hot plasma, you can also have CMB photons that backscatter off of it through inverse Compton scattering. And so you get this SZ millimeter effect, where you can also see that the galaxy clusters are bright in millimeter radiation. Likewise, the center of the galaxies contain, of the clusters contain galaxies, and so you can see the structure of the galaxies in optical light. However, because these galaxy clusters contain a lot of astrophysical shocks, so like dissipating shocks due to turbulence, or shocks produced by cluster formation or structure formation, and also by internal objects like supernovae, winds from galaxies, and AGN, you get this non-thermal component that we see in radio, and that's due to synchrotron emission from the relativistic electrons that interact with the magnetic field. So what I'm going to talk about is, instead of going into a lot of detail about the non-thermal cosmic ray electron emission, I'm going to talk about, I'm going to focus on more of how the hadrons, so the relativistic protons, can actually give us some non-thermal emission in the form of gamma rays. And then I'm going to describe a model that we developed to try to explain the gamma ray emission observed in galaxy clusters with a focus on Coma, and then talk about our results and implications for how cosmic rays diffuse or propagate through the ICM. Okay, so just a quick primer on how you can accelerate electrons and protons and ions to relativistic speeds and generate these cosmic rays, is that basically if you have a shock, so let's say supernovae or shocks due to AGN, etc. What happens is that you're going to have a Maxwellian distribution of the particles, and they'll follow a Maxwellian distribution, but you have this tail end of high energies, and these particles can go back and forth across the shock as the shock moves through the medium, and due to the deflections of the magnetic field, will be each kick through the shock will actually bump it up in energy, and so you can actually accelerate these particles to relativistic speeds before they escape the shocks themselves. And so this is charge dependent, so all you need is electrons, protons, or ions, anything with a charge, and they can be heavily accelerated. And it turns out that actually the acceleration efficiency, so what fraction of that shock kinetic energy goes into accelerating cosmic rays, and also the energy cutoff, is dependent on the Mach number of the shock itself. And so in galaxy clusters, you could expect a lot of possible sources. These include supernovae, accretion onto AGN, accretion onto the cluster itself, and also mergers. So anything that can generate these astrophysical shocks should be able to accelerate charged particles to become cosmic rays. And so the nice thing about Fermi, since it's looking at the majority of the sky, it's looked at many different galaxy clusters. And you would expect that to see this non-thermal gamma ray emission due to the relativistic protons. And that just arises when you have relativistic protons or cosmic ray protons that are moving through the intercluster medium, and they're going to collide with the ambient thermal protons in the ICM. And that gives you a sequence of events where you have two protons collide, you create mesons, so typically pions and other types of mesons, and a third of those reactions will give you neutral pions, which then can decay into gamma rays that we can see with Fermi. And so although this is just upper limits for 50 galaxy clusters observed by Fermi, they predict that about 1% of the energy, or the cosmic ray energy density is about 1% of the thermal energy density of the ICM. And just like to note that this was taken with many years of data, and the longer Fermi is looking at these clusters, you will get more significance with these measurements. So, there's been many studies that have shown that galaxy clusters should actually be kind of gamma ray bright, and that's just because you should generate a lot of cosmic ray protons that can then diffuse through the ICM, and then as they collide, and then the ICM itself, the protons in the ICM, act as target material. And in fact, this work by Pinsky and Fromer suggests that you expect the gamma ray emission in galaxy clusters, at least within the virial radius of the cluster itself, should actually be dominated by the pion decay over the secondary and the primary electrons. And so for the gamma ray emission for electrons, that's just due to inverse Compton scattering on the CMB photons that can accelerate, that can scatter them up to gamma ray energies. And so you have this primary component for electrons for the primary electrons that are produced in these shocks, but then also because of the pion decay, you get a secondary population that's a bit weaker. But what matters most, I think, in this plot is just to pay attention to the fact that the pion decay within the cluster should dominate the gamma ray emission. So Fermi has been looking at the Coma cluster for 9 years, a little over 9 years now. And so the nice thing is that the detection significance has been going up. So now it's, I think, we have Katie Ashetel over at OSU has been analyzing the data for us and is making us maps and will give us an updated value with the diffuse emission from Coma. And so she says, give it a few more years and there'll be a 5 sigma detection. But the nice thing is we can at least use these upper limits to constrain cosmic ray proton properties in galaxy clusters. So for example, the upper limit for Coma from the 2016 Fermi paper suggests that it's about 5 times 10 to the 9 photons per centimeter squared per second. And so this is actually kind of dimmer than what you would expect if the cosmic ray protons had similar properties, propagation properties like in the Milky Way. So the Milky Way is actually, the halo is actually gamma ray bright, and you see this nice isotropic diffuse emission. And that has led many to discover that the mean free path, the time or the path between scatterings on the magnetic fields is actually about 1 parsec, and so you can get this bright emission. However, there's a couple explanations as to why we haven't officially detected gamma ray emission in these galaxy clusters, why it appears to be dimmer than you would think. And that just depends on either how well the cosmic rays are contained within the cluster, and also how efficient are the sources able to accelerate these cosmic rays. And so you get this degeneracy in these two effects. So one way to think about the containment of these cosmic rays is to look at how they propagate through. And you can describe the propagation of cosmic rays throughout the cluster, via through diffusion. And then, of course, the escape time depends on the diffusion coefficient and the size of the cluster itself. And then the cooling just really depends on the structure of the ambient medium that these cosmic rays can interact with. And so what I'm showing here is just a ratio for Coma, where you just showing the cooling time with respect to the escape time. And so basically above that line, you expect the protons, to be able to just escape before you have significant destruction of the protons and a lot of gamma ray emission. Or another possibility, because this of course depends, the emission is going to depend on how many cosmic ray protons you have, you can also have low injection efficiencies that can explain why we see this low emission. And so over here, I'm just kind of showing the gamma ray emissivity, which depends both on the spatial distribution of cosmic rays within the cluster and also the cooling time. So it depends both on the cosmic ray distribution and the target material distribution. Okay, so these two ideas has led us to develop a model to explain diffusion in galaxy clusters to understand the low emission in Coma and other galaxy clusters observed by Fermi. And so I'm going to discuss the motivation for that model right now. So we decided to develop a 1D diffusion model, and this is optimistic in the sense that usually when we talk about diffusion of cosmic rays, it depends fully on the properties of the magnetic field structure, right? However, the nice thing is that since the MHD turbulence in the ICM is highly super-alphanic, so just looking at this figure here, that kind of just shows you how the perpendicular and parallel diffusion coefficients should depend on the magnetic field structure, or on how alphanic the gas is. So, for example, if you're subalphanic, then what happens is your magnetic field structure is basically dominated. The mean field is dominated by this, parallel component, and so you're just going to gyrate or move along the magnetic field lines, the mean magnetic field lines. But as you become super alphanic, your field becomes more disordered, and so your perpendicular diffusion coefficient is also going to become stronger, and so the motion or the diffusion of the cosmic rays will become basically isotropic. And so that allows us to model this with a 1D diffusion equation. And like I mentioned before, we have this degeneracy between the diffusion, so the mean free path of the cosmic rays, and also the efficiency or the energy injection of the cosmic rays into the galaxy cluster. And so what we do in our models, we set those as two free parameters to try to see how we can constrain those two parameters. And so here I'm just kind of showing the diffusion equation that we're solving. We can vary dE, which the mean free path is proportional to that. So larger dE just means that we have a larger mean free path. And then the resulting distribution is going to depend on where the sources are, so how the sources inject cosmic rays into the ICM, and then also how they cool. And we model the ICM with just a beta profile, and the values that we use is applied directly from Coma data. And so we consider a variety of sources. The first is accretion onto supermassive black holes. So we take into account the fact that Coma hosts a very massive supermassive black hole and the brightest cluster galaxy at the center of it. It has about 2 × 10⁻⁻10 solar masses. And then we assume that that black hole is accreting at a fraction of Eddington, and we let that fraction of Eddington also act as a free parameter because that's not well constrained. And that some fraction of the accretion luminosity is converted to accelerating cosmic rays in the shock, because the accretion of the black hole is going to drive a shock that propagates out, in the galaxy, outside the galaxy, and then you get like a low Mach number shock interacting with the ICM. And we just model that as a very narrow Gaussian at the origin. We also take into account accretion by the virial shock. So, galaxy clusters grow over cosmic time by accretion of material, and then as that material falls into the galaxy cluster, it's going to shock at what's known as the virial radius, and then that's going to, and then in that shock you can accelerate some cosmic rays. And the Mach number of virial shocks have been shown to be from simulations about 2.5 to 4, so a little bit more supersonic than AGN accretion. And so we take our M-dots from Fakori et al., so from their work where they looked at accretion onto halos in a cosmological context. And here we also model this as at the accretion shock, we model it as a Gaussian but centered at the accretion radius with a thin dispersion. And here what I'm showing just to kind of show is that the paper came out this year that actually suggests that using Fermi data and also Veritas data, that they do detect an accretion shock around high energy emission around the virial radius of Coma, suggesting that this is a viable candidate for accelerating cosmic rays. And then finally, we also take into account supercluster type 1a supernovae, intercluster type 1a supernovae. And because in these galaxy clusters, galaxies are constantly being ripped apart due to mergers and accretion, you can have a significant fraction of stars that will eventually explode as type 1as just be put into the intercluster medium due to tidal stripping. And so previous studies suggest that about 20% of all intercluster type 1a should actually blow up in the intercluster medium. And these have much lower, factor of 2, so about Mach numbers of 10 in the ICM. And then the way that we kind of account for the number of supernova explosions in the ICM is to assume, and this is a very optimistic assumption, is that most of the mass in the intercluster medium, so the iron mass, is due to intercluster type 1a supernovae, because those will dominate the mass, the iron production. And then we model it as just a beta profile, where we take beta equals to 1, and from that, take into account that each supernova gives off about 10 to the 51 ergs. We can then take into account what the energy injection of that is. And one thing I should also note is that for each source, we have this ratio, this epsilon here, that takes into account, that kind of says what fraction of the kinetic energy from the shocks produced by these processes actually goes into accelerating cosmic rays. And we treat them differently for each, because these are different types of shocks with different Mach numbers, so the efficiencies aren't necessarily the same. And so taking into account our sources, and then solving the diffusion equation, we can easily kind of derive what the spatial distribution of cosmic rays should be in the ICM. And so here I'm showing, assuming the same efficiency for all sources, 0.1%, and assuming that the AGN has been accreting at 10% of Eddington, you see that the profiles are somewhat different because the energy injection by supernovae is the weakest. We see that the energy density of cosmic rays is lower than the other two sources. But of course, all these values are going to change drastically based on the efficiency. This is just kind of to guide the eye what the spatial profiles could look like based on these different sources. Okay. So once we have the number density, and we know the density structure of the ICM in Coma, for example, we can then try to figure out, okay, well, what efficiencies are required and what mean free paths do we need for cosmic rays to explain the diffuse emission or barely detectable diffuse emission of gamma rays from Coma. And so with the number density of cosmic rays in Coma, we can then calculate the emissivity, which depends both on the gas density profile and the distribution of cosmic rays. And with that, we can then calculate, we can integrate over that and calculate what the expected fluxes are for a variety of mean free paths and efficiencies. And so that's what I'm showing here. So this is for the gamma ray flux from the virial shock. And what I'm showing is a contour plot that shows the different fluxes you would get for a variety of mean free paths for the cosmic rays, and also for the acceleration efficiency. And then the black line is the constraint from the Fermi upper limit. So basically, you have to be on this line or below from the Fermi limits. And using the results from the Kishat paper that came out this year, they say that about 0.03% of the accretion energy can actually explain the emission that they observed. And so that suggests that if that's true, then that means that you would expect this can be explained by a mean free pass of about 100 parsec to 1 kiloparsec. Likewise, for most optimistic conditions for type 1a supernovae, you find that if you take the galactic value and apply it for the efficiencies of accelerating cosmic rays, and applying that to the intercluster supernovae, you find that to kind of go along with the upper limits from Fermi, you also get that the mean free pass should be 100 parsecs to 1 kiloparsec. But this is assuming that one of these sources actually dominates the gamma ray emission. And then finally, this is the most uncertain because we have two factors, the fraction of Eddington that the AJN is accreting at, and also then also the efficiency for it to accelerate cosmic rays, and then lower Mach number shock, which I haven't found anything that has constrained this yet. But you can see how much it varies, how much the efficiency varies based on the accretion rate onto the black hole. But I think the main takeaway with all this is the fact that in order to explain the diffuse emission or lack of detection of gamma rays in galaxy clusters, you expect low efficiencies or long mean free paths or a combination of both. And so just to talk about some of the implications and the caveats, but so this is ongoing work. I'm working on this right now. All of these sources can easily explain the low gamma ray emission or the upper limits of the gamma ray emission in Coma and potentially other galaxy clusters. But it's still uncertain which one of these processes would actually dominate. And so we definitely need a lot more work done on acceleration efficiencies for different Mach number shocks. The cosmic ray mean free path, and also so therefore the diffusion coefficient is likely larger in the ICM of galaxy clusters than the galactic values that we refer for the Milky Way. And this just might be due to the fact that the gas properties are different, the magnetic field is different outside our galaxy, rather than when you take into account the turbulence in the ICM as a whole. Like I said before, we still require lots more Fermi observations, so probably a few more years until we get that significant detection to say that there are gamma rays in Coma. And so this is still going to be ongoing work. But one of the problems too is, Fermi, as you get to lower energy, so Fermi goes all the way down to about 20 MeV. The flux I quoted you was 100 MeV to 10 GeV. When you want to look down at the lower energy ranges, the point source function actually gets much broader and becomes about the size of Coma itself. And so it's going to be hard to be able to really follow the spatial distribution of gamma ray emission from these types of galaxy clusters. And so there's more work to be done. So this was just a simple, apply a 1D model to get a better idea of what is the cause of the gamma ray emission in galaxy clusters, and we'll be extending stuff to 2D and so on later. So thank you.
is something where stacking would be useful. Has someone done the Fermi data?
You mean for the individual galaxy clusters? I don't know what they have for like stacking all 50 together. Yeah. The thing is that I think too, it also kind of like, so for example, the paper that I showed you, actually, I haven't seen that for the Fermi data. Because the gamma ray emission could be slightly different. But yeah, I think you're right that if stacking it would give you a better signal, of course.
And if your regime of no detections, then
Yeah. I'll have to talk to Katie about that because she's the one that handles all the data. Oops.
There are also intermediate measures of energy, say by at Earth to Earth Balancement and by integral.
Mm-hmm.
So these observations around 100 keV, can they tell you anything?
So for the hadron origin, you have to look at above the MeV bump, which is like from the pion decay, which is I think about 70 or 80 MeV. So they really have to look at the 100 MeV and above. And then the lower energies will actually trace the leptonic gamma rays, so produced by inverse Compton scattering from the relativistic electrons. Yeah.